In this lesson, we're going to look at the idea of an inverse transformation. That is one that undoes the effect of a transformation. So it takes you back to the original point. We're going to look at how do we find the matrix associated with that particular transformation. So first of all, we're going to consider whether we can find a matrix A that satisfies this property. So 2 minus 1, 3, 1 times the matrix A would take us back to the identity. And also A times 2 minus 1, 3, 1 would take us to the identity. So A, we're looking for A to be an inverse transformation to that matrix there. So one thing we could do is we could try to solve this using simultaneous equations. So we could call A, B, C, D. And we could say, if we expanded out 2 minus 1, 3, 1 times A, B, C, D, that would equal the identity 1, 0, 0, 1. So multiplying that out becomes this, and we can then compare each of the elements to give us 4 simultaneous equations. So the top left gives us 2a minus c equals 1, top right gives us 2b minus d equals 0, and then the other two at the bottom give us those two equations there. So we can solve those by solving the first and the third to give a and c, and the second and the fourth to give us b and d. The values that we get when we solve those are a equals a fifth, b equals a fifth, c equals minus 3/5, d equals 2/5. So putting those together gives us that matrix A is given there. Now we could bring out a factor of a fifth, so the elements inside the matrix are integers. That just makes it a little bit easier to work with. So A could potentially be an inverse matrix for 2 minus 1, 3, 1. We would just have to check that it worked the other way around as well. However, there is a quicker way of doing this. I'm going to look at that now. So if A is a square matrix, we can define the inverse matrix as A to the minus 1. And because they are inverses of each other, we know that A times A inverse and A inverse times A will both lead us to the identity matrix. So there is a formula for finding that. For any 2 by 2 matrix, if we define it as A, B, C, D, the inverse can be found by, first of all, finding the determinant of A, B, C, D. Remember, the determinant is AD minus BC. I'm going to put 1 over that determinant at the front. We're then going to change the order a little bit of the elements inside A. So A and D are going to swap places. B and C are going to stay in the same place and multiply by minus 1. So the inverse matrix A is the determinant, 1 over the determinant of A times D minus B minus C A. Now, a matrix wouldn't be able to have a determinant, an inverse, if the determinant was 0, because 1 over 0 is not possible to calculate. Any matrix with a 0 determinant is called a singular matrix, and singular matrices do not have inverses for that reason, because we can't divide by the determinant. So let's define matrix A as 2, 5, 3, minus 1. Firstly, we'd like to find A inverse. So pause this slide and write down A inverse. Okay, so the determinant of A, first of all, is going to be minus 17. It's going to be minus 2, minus 15. So the beginning of the inverse is going to be minus 1 over 17. We're then going to shuffle around the elements inside the matrix to get minus 1, minus 5, minus 3, 2. So that is the inverse of A. The minus 1 over 17 could go inside the matrix to give fractions as the elements if we wanted to. I'm now going to calculate the determinant of each of those, so the determinant of A and the determinant of A inverse. Don't forget the minus 1 over 17 when you're calculating the determinant of the inverse. So pause this slide and calculate the determinants of each of those two matrices. So the determinant of A we already know, it was minus 17, and when you calculate the determinant of A inverse, you get minus 1 over 17. So that leads us to the rule that a matrix and its inverse have got this connection between the determinants. Determinant of A is 1 over the determinant of A inverse, as long as the determinant of A is not 0. Another way of thinking of this is that if you multiply the determinant of A and the determinant of A inverse together, you will always get the answer 1. They are reciprocals of each other. I'm now going to define two more matrices. A is 1, 3, minus 1, 5, and B is minus 3, 3, 4, 0. I'd like to pause this slide and work out the inverse of each matrix. Okay, so the inverse of matrix A is given there. It's an eighth of 5 minus 3, 1, 1. And the inverse of B is minus a 12th of 0, minus 3, minus 4, minus 3. So we're now going to calculate these three things to see if there's a connection between those. So first of all, we're going to find the product A inverse times B inverse. Then we're going to find the product B inverse times A inverse. Remember, they won't always be the same because matrix multiplication isn't commutative. We're then going to find the product AB and find the inverse of that answer, and that will give us AB inverse. So pause this again and write down those three things to see if you can see a connection between them. So the first product, A inverse B inverse, is given there. The second product, B inverse A inverse, is given there. See that they're not the same. And then AB multiplied together, and then the inverse of the answer gives us that matrix there. So you'll notice that AB, all inversed, is the same as the product B inverse A inverse. And it turns out that that works with all square non-singular matrices. So the rule is AB, the inverse of that, is the same as B inverse A inverse. Notice that the order has switched. So from AB, it's going to be A. Sometimes it's possible to find an inverse transformation in words just by considering what the geometrical interpretation is. So I'd like to pause again and just think about each of these three transformations and think about what the inverse transformation would be. In other words, if a point was transformed by the first transformation, what transformation would be needed to take it back to its original point? So rotation 45 degrees clockwise about the origin. To undo that, to take you back to where you were to start with, you'd need a rotation 45 degrees anti-clockwise about the origin. So they are inverse transformations of each other. Second one, a stretch factor 5 in the x direction. The inverse of that would be a stretch in the x direction factor 1/5. That would take you back to where you'd started. And finally, a reflection in the line y equals 2x. The inverse of that would also be a reflection in the line y equals 2x. That's because all reflections are self-inverse. If you do a reflection and then the same reflection again, you'll always end up back at the point that you started at. I'd now like you to complete exercise 7D on page 155.